The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so let's get started. Today we're going to be talking about Preflop, which is the last thing I definitely want to cover before the Sakuna tournament. As you know, this is going to be one of my last lectures. I'm teaching one or two over the next 2 weeks, but we're primarily going to have guest speakers talking about, I guess, more the macro poker environment. Okay, cool. So why are we doing Preflop? So in tournaments, most of your value is going to come from what you do pre-flop, playing it close to optimally. And the reason is because a lot of people don't do this good at all. Like they really play pre-flop badly because it's very counterintuitive, especially live. Like live, people have a much tougher time doing this because either like they're afraid of getting knocked down on a bad hand, or they're afraid of showing down a bad hand, or live players are just worse in general. So for whatever reason, people screw this up online a little bit, on live a lot. In addition, one of the reasons that we're spending an entire day on it is it's relatively easier to solve from a mathematical standpoint. Like we can get close to like a Nash Equilibrium because there aren't that many variables, whereas like post-flop, there are a million variables. It's more related to kind of putting things into patterns that you might be close to. So that's why I'm doing this. And then let's start with the scenario that we're going to be analyzing for the rest of the class. There we go. Okay, cool. So here's our scenario. So how it works heads up is the dealer button is a small blind. That's a like slight break in the rules because you would assume I'm button, he's small blind, I'm big blind, but they change it around a little bit. This way the button isn't the last one to act every round. So here I'm first one to act pre-flop and then last to act every round thereafter. If I were big blind, I would be last every single round. So that's a minor variation that you guys should just know. Situation, I'm small blind for 125, he's big blind for 150, and there's a 25 ante, which is why there's 50 in the pot. And the question is, what do we do here? Okay, so we have 9-6 offsuit with 2.5 M. We're in the small blind, and we're trying to figure out what do we do. So the answer here might not be that intuitive, and I don't think I give it to you right away. But how we figure it out is just with a normal semi-bluffing equation. We take a look at, okay, so everything pre-flop is a semi-bluff because like we have some chance of winning and we're virtually never less than 30%. So we just use this semi-bluffing formula that we've seen before, where our EV is just going to be the pot times the chance he folds, plus the chance he doesn't fold times our like EV when he calls. We need to figure out some sort of calling range. So I just made up one here that seemed like about at the pro level, and this is pretty wide, right? Like him calling with like ace-2 or jack-10 or 2-2. Like this is a wide-ish range. I think a lot of players for the tournament life might not call this wide, but it ends up being like 27.6% of hands he's calling. So we're going to use that as a baseline, and then later we'll show why that doesn't matter. So our question is, what's our equity versus his range here? And what we can do there is just plug it into Poker Tracker. So the idea is we don't know what hand he has, and we don't care. Like it's unrealistic to think that we can get down to any sort of hand he'll be calling with, but we can get down to a range. We can say he's equally likely to have any assortment of the hands in that range, because like if he calls, that means that he has one of those hands, so we can compare our equity versus any one of those hands to get our equity versus his range. And we can do that in Poker Tracker. So what you're going to do is you're going to open up the equity calculator, you're going to put in 9-6 off, and then you're going to put in this. I actually just drew it in there, but that's the same thing I showed before, which is pocket twos are better, ace-2, king-2, queen, or king-10, queen-10, jack-10, and then the same for offsuit, which is the representation of this entire thing. I just didn't separate offsuit or suited, and then I assumed by jack-10 it meant like that entire corner, although Poker Tracker likes specifying. Anyway, so this is our equity versus this. This is saying that if we go in with 9-6 and he calls with anything in that range, we are 34% to win this hand. So I don't know if that's about what you would expect. it seems higher than like I would have thought initially, but that's our equity versus range. Like if we go all in and he calls, we can assume we're a 35-65 underdog without even knowing what he has. And then once we find out what he has, we'll find out whether we're slightly better or worse, but that doesn't really matter. So we can calculate our EV in this hand in the same way that we're used to calculating semi-bluffing EV. The EV of the push is going to be the chance of him folding times 425. If he calls 27% of the time, that means he folds whatever this is, like 73% of the time. So that's our like value from him folding, the fold equity. And then 27% of the time, we're in a showdown situation where of that like portion of the time that it calls, we're 35 to win 1250 and we're 65 to lose 950, resulting in a total equity of 253. So that's a lot of chips for what might seem like a very marginal move. By going all in here, you're actually making that many chips. And in fact, like a more provocative way to describe it is, if you don't do this, you are losing 250 chips. Like you only need 1,000 to win this whole tournament, and by folding this like what seems like a very weak hand in this position, you are just giving him 250 chips of value. So that's a lot, and that shows how counterintuitive this is. That a situation where you have really bad cards, you don't realize that these are actually really, really good cards in this situation. In fact, no matter what your cards are basically good in this situation, because the situation makes any two cards good enough. So let's talk about, so we made one assumption, which is what his call range is. Do you have a question? Oh, okay. So we made some assumption about what his call range is. And I said it didn't matter. Why? Because what we can do here is make the call range a variable, right? So this fold percent is a variable, and then our win percent is related to the percent that he folds, right? Because like if he calls a small range of hands, when we get called, he's going to be crushing us. Whereas if he calls like 90% of the time, we're probably ahead of his range because he calls a lot of worse hands. Anyway, so you can take a graph and just look, okay, he calls somewhere between 0% of the time and 100% of the time. And then we can do this EV equation for all of those hands by calculating like, okay, so what's our equity versus his calling range? This doesn't change. We still win or lose the same amount every time. And say, okay, so if we're always pushing here, if he calls with whatever range, this is our EV. And then one thing that's interesting about this graph is what? It's always positive, which means that no matter what his calling range is, this push is good. It might be more intuitive this way. Like if he folds 100% of the time, if he only calls 0% of the time, we trend up to a number around here. And what number is around here? That's just this. It's the pot before we do anything. So if he folds 100% of the time, we just win the pot. Like that's our EV every hand. And it just trends based on this, where the more he calls, typically, the worse our EV is going to be. Yeah?
So this is true for 9-6 offsuit.
Yeah.
What's like the lowest pair for which it's still positive?
We'll get to that. And that's a good question. Although it's going to take us like half the class to answer that. Anyway, so that's the cool thing here. So it's always positive, which means like I'm saying no, like even like no matter what the villain does, always push all in with 9-6 offsuit in this position. Okay, so let's break it down into components. So to explain intuitively what drives this graph is your equity there is split into two parts because it's a semi-bluff. It's your fold equity and your showdown equity, right? So let's turn this into lines. So you see your fold equity just decreases the more he calls in a linear fashion, right? So that should be fairly intuitive. Like the proportion he calls like reduces your fold equity by that amount. And then your showdown equity has a little curve here where you get more value from the showdown on average the more he calls. The only reason there's a little bit of curvature is because this is multiplied by the chance of him calling in the first place. So it's tilting. It's tilting in some direction. But anyway, that these are curved makes this a very interesting optimization puzzle. And the reason we're positive at the end is for this reason. Like we're basically, so this line, the total equity, is just the sum of these two. where our showdown value is going to be negative over basically the entire range. And even when our fold equity reaches 0, that's when our showdown equity creeps just above 0. Regardless of what his calling range is, your average is like 175 chips of EV. Like the 20% calling, or whatever we said, the 27% calling range isn't necessarily optimal if he knows you have these cards. But on average, you're getting like 100 and something chips. And just to show how bad it is folding, like if you just open fold this for some reason, that's as bad as purposely calling it all in with 3-4 versus ace-king. Like that's an equivalent amount of EV loss as folding this hand. Okay, so now let's talk about how hard this is going to be. So push-fold decisions are really hard to kind of intuitively figure out just because of that, like the curvature and then the steepness of those graphs are moving in kind of weird directions, and they're both moving at the same time with regard to all the other variables. So it makes it so that it's very hard to come up with very quick rules. Some variables that are going to affect our decision, and the result is either push or fold. Like our result isn't even as complicated as bet a certain amount, but the variables we have to consider are our cards, our position, our stack, and the villain's call range, which results in like this 5-dimensional array that we have to kind of slice and dice so that we have our push-fold decision range. So what we want to do is isolate for specific things. We want to say like, okay, let's make this and this static so that we can solve for these two. Or let's make these two static so we can solve for these two. So we can end up with a chart that looks something like this. And this is a little bit more manageable. We could just say, like this green area is when you should push, and this yellow area is when you should fold. Like that's our goal here, to be able to develop that sort of chart, and then figure out what's the best thing to isolate. So let's get to it. So a range is just a poker set of hands. This is how you write it. This is the assumption that we're making. So we're doing it for two reasons. Analyzing our opponent, which we're not going to be doing. We're going to assume we have no information about him because it's pre-flop. And a lot of it, one of our assumptions is that he hasn't even acted yet, so we have no information at all. But we're going to be using it to determine our plays. Basically, we're saying we have some sort of decision rule for a range. Like we certainly can't solve this for every single hand, or at least we can't remember it. So what we're going to do is come up with a line where we say every hand above that certain line, i.e. that range above that line, is going to be good for our specific decision. And we're bringing these into percentiles, and that's how we're going to describe them. And we're using Sklansky-Karlson, his rankings for our breakdown of percentiles. But here's his original question. And this is just to explain where these come from and why this is particularly relevant to what we're doing. So his question is, you're the small blind and you have a choice between either folding or open pushing a hand, or open pushing here means you push and you show your hand before he makes a call. And the question is, like, how many chips is this good for? If you have one chip, or I guess if you have two chips, like you have, since there are 1-2 blinds, if you have two chips and one is already in the small blind, your pot odds are 25%. So even if he knows, like he's going to call if he's anything more than a 50% favorite. So you have the odds to do that with at least a pretty bad hand and a lot of good hands. So X here is like, how big can your stack be before this starts becoming unprofitable? And the answer for ace offsuit is about 70. And to explain how we got to that is we're going to make a couple assumptions. And you can see the clear relation between this like methodology and what we're doing. Okay, so 1-2 blinds, hero small blind with whatever, hero bets X all in, and we're going to say big blind's going to call when EV is more than 50, which he might do like pot odds, which we're just going to ignore now for simplicity. We're just going to say big blind is calling when he's more than 50% to win. It's actually 0 when he has a pot odds, which is this equation, but we're going to forget about that. Let's just say he's going to only call with literal better hands. So here he's going to call with ace-8 or pocket twos, right? Because we have ace-8. He's going to call it the pocket pair, which is always going to be better, and ace-8, which is going to be equal or better, right? So that's his calling range 13% of the time. So we win 33% versus this range, which is like you just plug it into the poker tracker, and it'll give you that you're a 33% underdog. Oh, which is what I did here. Like that's how you do it. And we can get our EV from this situation. and we have to solve for x. So we want EV to be 0 because we're finding the marginal EV, and this is what we get. We get x, which is all of the chips we had before we paid the big blind, and we lose x minus 1, which is all of the chips we have after paying the small blind. So a little bit of nuance there. It only changes our number by 1, but that gives us our break even. And our break even here is like 62x. So the reason it's a little bit lower is it doesn't factor in the big blind doing pot odds, but that's the idea. Okay, so what we're gonna do is we're gonna solve this, and we're not gonna do it, someone else did it. We're gonna solve this for every single hand. And this is what Sklansky did. Okay, so he figured what your number here is going to be 2 things. The number of hands you are at least slightly better than, and why is this factor important? What's he gonna do if you have a better hand than him? He's gonna fold, right? Okay, so this determines like our fold equity, and then chance of winning when you're behind determines our equity when he actually does call. He just has perfect information, which is why it's a little bit of a change, and we're able to solve it out, I guess, perfectly here. Okay, so Sklansky didn't know how to program, which is why this guy Karlson, or Viktor Chubukov, a couple days later, apparently later the same day, came up with the answer. We said aces have an infinity value here, where like no matter like you can have an unlimited amount of chips and then show aces and then push them, and it's plus EV. Like, we're not saying it's the most optimal decision, but you won't actually lose chips on average, even if you have an unlimited chip stack. Whereas kings, it only works for 1,290 chips. So we can solve it for every hand to get down to like, you can do this with 3-2 off with 1.8 chips and so on. So this is our primary way to rank hands, and we're assuming that, at least in a heads-up situation, this is a pretty good idea of what hands will have the most value, especially when it comes to going all in. One other method is going to be equity versus 3 randoms, and it might be more relevant for multi-way pots. It's just, you just rank them by their expectation against 3 callers who haven't looked at their hand. But we're not going to do that, especially because we're assuming generally we're going to get 1 caller, especially heads up, where you can only get 1. But we're going to expand it out later. So just an example of what these are: top 1% is aces, top 5% is 10s and ace queen, 30% is this. And sorry to bring it to you guys, but you're gonna have to memorize these. So 5%, you just remember their premium hands, which is 10 or ace queen, and I'm giving you little mnemonics to help you remember it. Like ace 10 or better is 10%, and then like some sort of pocket pairs, it's not even that big of a deal if you go down to 2s here. 20% is ace 2 or pocket 2s. That's how you're going to remember it. And then 30% is Broadway. So Broadway is any 2 face cards. And like an intuitive way to think about it is based on this. Like Broadway is just this corner here, which is about like 1/3 of the graph when you count in like pocket pairs. So that's how you just remember 30%. It's that corner. So it's not that bad. Just remember top 20% is ace 2 and 2s, 30% is Broadway, and then like 10% is ace 10. Not that bad. So 50% is just going to be the diagonal on the graph. It's any 2 cards adding up to 15. So like, this is what I mean by the diagonal. Like, this is your 13 by 13 graph, where these are offsuit and these are suited, which is why we double count them. And then this hand adds up to 15, ace 2, and so does king 3, and so does queen 4. So this is your 50th percentile hand. So that's how you're going to remember that. And then you don't really need to remember anything more than that. So 100% is going to be any 2 cards. It's going to be the entire graph here. Okay, so we're going to be talking about, yeah?
What is the percentage stand for?
Percentage is the percent of hands that range represents. So like, this is the top 10% of hands. So if he calls, if we assume he's going to call 10% of the time, we are saying that he will call with these cards and these cards only. And we're going to be talking about ranges from now on, because it helps us understand what cards he has to some extent, but also lets us use it as an idea to get to figure out exactly how often he's going to call. So we're just going to be talking about ranges, and this is what I mean when I say ranges. And to the extent that you're just doing this at the table, you just have to memorize like these 3 numbers, because this is easy, and then just remember that 10s are 5%. Okay, so when we're talking about ranges in general, a plus EV range, a decision that's good for a range, means that on average, your decision is profitable for every for that range in general. But an optimal range is profitable for literally every hand. So like you can do a lot of things that are profitable for any two cards, but 3-2 off might actually not be profitable. So it's not necessarily optimal. You want to make sure that to the extent you can, every single card in that range is optimal and is profitable, which gives you the optimal range. It's the most plus EV range for that type of decision. An example of this is like, okay, so say you're playing against ace queen and you call with this range, pocket fives and ace 10 or better. So you are ahead of this range of ace queen because you're 53% to win the hand with this range. However, we know it's not optimal because we are calling with two losing hands, ace 10 and ace jack. So a more realistic, like a more optimal range is going to be like pocket twos and ace king or better. So that's going to be the difference there. So I want to make sure we're not solving for something that's a slight favorite when actually missing out on something a little bit more optimal. Here we go. So this is a better range. 5-5 or ace queen, actually twos or ace queen would be a little bit better. And we win 60% of the time. And then if a range is optimal, then we know for every hand in that range, we have a plus EV decision. And that's why this is like the axiom we're going to use to prove that if we solve for a range, then we know that if you have any card in that range, our rule is still good for it. So that's why I'm showing you that. All right, so that's it. So that's all we're going to do in terms of defining what ranges are and how we got those numbers. And from now on, we're going to talk about making decisions based on a range. So let's talk about preflop. So our assumption is hero has M less than 10. Like we're in that period of the tournament where your M is not going to be that high. The villain is calling some percentage of hands that are presumably the top whatever of hands. We're guessing he's not calling with worse hands than and folding better hands. Like I think that's a reasonable assumption. He might be a little bit, like his view of what are good hands and bad hands might be a little bit off of ours, but we're just assuming everyone has the same. ICM doesn't matter, so we don't care about payouts in tournaments. We're just trying to maximize our chip EV. And we only have two decisions, push or call. Okay, so the way that we're gonna come up with this rule here for heads up is, so what we're doing is we wanna figure out what our push-fold range is for heads up in every scenario. And the way that we're gonna do this is, first we need an equation that tells us range for range equities. So everyone can kind of like figure out like aces versus whatever is like 80-20, and then two overcards with a pocket pair is like 50-50-ish. But we want to know what's a range versus a range. Like if we push 70% of the time and he calls 30% of the time, like what does that translate to in terms of our equity? And it ends up being like 60-40, but we want to get an idea of what that trend is because that's going to materially change our ability to come up with an optimal solution here. So we want to build a table of range versus ranges, and then we come up with a formula that will let us put in two ranges and come up with an equity calculation for both of those ranges. Then we're going to develop an EV model for semi-bluffs, which we already did. So that should be quick. For each M, find Nash Equilibrium if one exists. So a lot of people, if you Google like Nash Equilibrium for preflop, you'll find something, it's wrong, and later I'll show you why. And then for unstable equilibriums, which it pretty much always is, find like a reasonable range and figure out what kind of assumptions we need to make our push-fold decisions correct. Okay, so let's do this first thing. So if we just, for each, say that we use a hero's range of 50%. So in Poker Tracker, we put top 50% of hands, and then for each range of hands for the villain, we calculate the equity for that. And we do that for whatever I did, like 15 different ranges. So if we push 50% of the time and he calls 50% of the time, what's our equity? Like what's our chance of winning? 50, right. Okay, so we have an even equity because we are pushing and calling the same types of hands on average. Whereas if he calls 100% of the time, our equity is actually closer to 60. Like we are the favorite, we're like a 60-40 favorite in that hand. Whereas if he calls with like just aces, then we are like 17% to win the hand. That's the idea. So what our goal here is to come up with some sort of equation that we can just plug into, like we can do math on. Like we want to be able to do calculus on it, so we need an equation. So like what type of function does this look like? Because we want to try to fit a curve to it. Exactly, like it seems like a logarithmic function. And in r squared of 99, it says that that's the logarithmic equation for it. So that works when the range is 50%, but let's take a look at when we change the range to 30%. So what this is saying is we are pushing 30% of the time, and he is calling X% of the time. And what this line is our chance of winning when he does that. And this is also logarithmic. So we're seeing a little bit of a pattern, and then it also has a really good r squared. And then if we push 10% of the time, it's still like okay, it's 98 and change when we look at our equities versus his calling range. But then it starts to get bad. If he calls 5% of the time, our r squared, when we fit a log normal function or a logarithmic function, is only 95. And if he only calls 3% of the time, our r squared is 89. Like this is not really logarithmic when we start getting in very tight ranges. And in 1% it sucks. Like it's not even close. So what we're trying to do is develop an equation for figuring out range versus ranges, and we see that logarithmic works some of the time. So the reason it doesn't work, just to give you kind of the idea of why it doesn't work, is because the top 1% of hands is like 3 hands. It's aces, ace, king, and kings. So it's materially changing based on whether he's, like if we push like ace king, whether he calls with only aces or kings or also ace king jumps us between like here and here. So we have huge gaps when it comes to very tight percentages. So that's why we break a little bit up here. And when we turn it around, we have the same type of thing. This is looking at, okay, say that we know he's going to call 50% of the time. If we push X% of the time, what is our chance of winning? So if we push 100% of the time and he calls 40% of the time, then we are 40% to win. So that's what this chart is telling us. And you see the same type of pattern where 50% range versus this kind of range is good. If we push whatever and he calls 30% of the time, it's still good. But then if he calls 2% of the time, it starts becoming bad. So what are we taking away from this? And the whole plan is we want to come up with an equation that just gives us these numbers. I only got these from pushing them into Poker Tracker, and we're trying to fit a certain equation onto it. So our takeaways here is that like range versus range relationship is probably logarithmic. Like that seems to be a good estimate, but it's definitely not good in the top 5%. So with regard to our model, we're just going to say this is probably not that good when you're talking about ranges in 5%. But realistically, when m is less than 10, no one is doing anything in the 5% range. So it's not that big of a deal just to ignore it. Okay, so what we did is we populated this table just now. So we took a look at what's the villain's range up here and what's our range. So when we push 100% of the time and he calls 30% of the time, we win 39% of the time. Where red means that we are not likely to win and green means that we are likely to win. Like when we push 5% and he calls with anything, we're 73% to win, right? So that's what this table's telling us. And what we want to do is we want to come up with an equation that lets us populate this table without actually having to do the range versus range calculations by hand. So what I did was I just ran a regression based on logarithmic variables, and I found out something that I found to be really, really cool. So these seem to be the coefficients with an r squared of like 98. So this equation seems to basically nail these range versus range equities, which is like, I think really cool. Like, so I guess there's probably a reason that it starts at 50%, and then it seems to be symmetrical, which is like, I don't know if there's a statistical reason for that, but that's extremely fascinating. And it could make sense intuitively that, so this is your chance of winning. So would it make sense that the wider he calls, like when we take the natural log of the percentage of him calling, our percent win goes up? So I think it does because it means he's calling with worse hands. That's why it goes up when he calls greater, but then goes down when we push greater, because this means that we're pushing worse hands. So that's the equation there, and that's giving us something that we can actually differentiate when we're trying to solve this. And just in terms of errors, like it's not that bad. Like we have an R squared of 98. So I think this is good enough to use. Like we can actually use this to try to optimize our decision-making pre-flop. So we solved, like we came up with an equation that we can use for determining our chance of winning a hand compared to our pushing range and his calling range. So let's go back to our EV model for semi-bluffs. So we already did that in the fold equity portion, but we're going to build this out to be relevant to our situation in particular. So we're assuming we're talking about in terms of M. So our blinds are going to be equal to 1. Like this means this is 1M, and our EV is going to be in terms of M's. Like we're going to, if our EV ends up being like 0.35, it means 0.35 times all the blinds combined, just to get rid of blinds here. So all the blinds combined equals M. Our showdown value is just going to be, okay, so our fold equity is going to be the pot times the chance of him folding, i.e. 1 minus calling. The chance of him, or our showdown value is chance of calling times win amount times win percentage minus lose amount times lose percentage. The win amount is going to be stack plus 2/3, because if the blinds are 1, 2 or something where the big blind is double the small blind, it means that you win his big blind and then you lose your whole stack. It depending on when we mark our stack, it changes it a little bit with regard to whether we count it as before we pay the blind or after, but it ends up not making a huge difference. It just impacts whether this is plus 2/3 or plus 1/3 or just your stack. But anyway, we also have this equation which we just solved for, where the chance of us winning is related to the chance of him calling and the range that we're pushing. So what you might see here is all of these are related to the same 3 variables, where it's either the call percentage, the push percentage, or a stack size. So we can combine this to one giant equation, which obviously we're not going to remember, but we can use to start solving this mathematically. So this is what we would end up with. So when M is 1, we end up with this sort of graph, when the hero's push range, which goes up to 100% here, and the villain's call range, which goes up to 100% here, this is our equity, which I just color-coded so we don't need to look at the numbers, where green means it's in the hero's favor, and yellow means it's close to 0, and red it means it's in the villain's favor. Okay, so what we see here is it's really green over here and really yellow over there. And this is telling us, this is already factoring in fold equity and our chance of winning if he calls. This is saying that if we call 100% of the time, he should call 100% of the time, because he wants the yellowest area and we want the greenest area. So that's with 1M. So it shouldn't be surprising that kind of our equilibrium at 1M is going to be everyone getting all in 100% of the time. But you see, when we switch to 10M, it's pretty different. In fact, this 100-100 is one of the yellowest areas, whereas our green area is either up here or down here. So we're going to use this to get an idea of how our value changes based on these variables changing, to figure out if we can isolate it to a corner and make that our kind of rule. So first, let's find out when we can get a Nash equilibrium. So the villain gets to pick this, right? The villain gets to pick his call range, and we get to pick our push range. That's the flexibility each person has. So if we push 100% of the time and he calls 100% of the time, this is a Nash equilibrium for 1M, because he can't do any better by going up here, because a higher number is worse for him, because this is our equity in the hand. And the equity comes directly from him because it's a heads-up situation, whereas we can't do better by pushing less. When we go down here, the next number is 0.32, meaning that if we push any less, we're actually losing value, because we want the number to be highest. And when it comes to 2M, 100% isn't that much off. We're talking about 0.01 M of a difference in EV, but we do actually reach a Nash equilibrium here at 2M, where we can't do any better by moving, and he can't do any better by moving. So when M is 3, we have an unstable Nash, and this is when it starts getting interesting. if we push 80, he should call 100, and if he calls 100, we should push 65, and so on. So we end up in a bit of a circle. It's a rock, paper, scissors situation once we have m equals 3. So this lets us know that this whole Nash equilibrium thing is not going to work out. Like, it only really works for m of 2, and that's not the most important situation to figure out, because you already know that you should be pushing a very, very wide range when m is 2. So we need to figure out some sort of pattern. Like, how do these colors move when your m is more than 2? So let's go to m equals 5 and make the gradient a little bit steeper. So these are the same numbers, except I just made it like we're talking about very slight changes in EV, where the difference between yellow here and like green here is like 0.1 m. And this will help us understand where this value is going to come from. So let's see how this changes over time. Because our goal here is, the villain's goal is to cause us to be in a yellow area, and the hero's goal is to cause us to be in a green area, right? And you can see why we inherently have this, this need to figure out what they're going to do. Because say that we're the villain, if we know the hero pushes 100, we call 100. Whereas if we think the hero pushes 30%, we should call 5%. So let's see how this changes over time. So this is when m is 2, and then this is us increasing as m is 3, 4, 5, 6, 7, 8, 9. We're trying to pick the box that's kind of the yellowest area. Like, where can we realistically come up with a rule for ending up there? Based on what this x coordinate is, what should be our like y coordinate? Like, what should be our call? Like, do we see any way to figure this thing out? So what I think we should do is just draw a line right here and say, let's just figure out what the equation of that line is, and then like come up with an estimate of what his pushing range is, and then throw it into whatever function we use to get that line, which can't be like very complicated, in order to make sure no matter what his pushing range is that we read him for, we end up in this yellow area. So what I did was, for each m, I highlighted what the lowest EV decision is for the hero, meaning the best decision for the villain. And for 10m, it's just diagonal. But for 1m, it's all the way down here. Like, best you can do is over here. So our function is, we call 10 times his pushing range. So if we have 1m and he pushes 5% of the time, we call about 50% of the time. If he pushes 20% of the time, we're calling always. And anything more than 20%, we're always calling. That's for m equals 1. In general, the rule is going to be, if m is 1, always call. And if m is 2, you call twice his pushing range. So if we think he's pushing 50% or more, we're always calling. If we think he's pushing 20%, we call 40% of the time. Like, that's the optimal calling range in this heads-up situation. So when m is 4, so I skipped 1, but when m is 4, we have basically the straight diagonal. We try to match his pushing range. So when he pushes 60, we call 60. When he pushes 100, we call 100. That's the best we can do to dominate his range there. When m is 6, we call 2/3 his range. And when m is 9, we call half his range. So those are the rules that we're just going to have to remember. When you're in a heads-up situation, if the stack is basically 1 or 2, you're always calling him. At 4, you're calling him an even amount. At 6 and 9, you're calling him like half of what he pushes. And like, that's the optimal move. Like, that is how you will, if you're in a heads-up situation, which you will be at the end of every tournament, to the extent that you like get there, like, you will dominate his playing style based on like what you read as his pushing amount. And you could just count like how many hands does he push versus how many hands does he fold to get an idea of what his range is here. And this also works when it's folded to you in the small blind. Like, even if you're 10-handed, by the time you get to the small blind, your head's up again, and these rules apply. So the extent that you can memorize this thing will give you the right move in that scenario for m's up to 10. Okay, so when you're the hero, when you're the small blind rather, and you're pushing, it requires you to kind of estimate what his calling range is, because you end up all over the place based on making different estimates of what he can call with, and you really don't have any information. But I'm gonna graph it out here, and then we can see what's gonna be a good estimate in basically any scenario. So there are a couple different ways I can think about this. So we're going to come up with a bunch of numbers based on the villain's call range here. And we can either, so we're targeting like a column, and then like the row is going to be information we don't have. So the question is, do we pick the column that has the highest average EV, the highest minimum EV, or the highest EV versus like a particular bad player that we're going to be targeting? And the blue here is what column maximizes your EV for that scenario. And like your guess is as good as mine when it comes to what's the best way to strategize it. Like, are we looking for like maximizing the min will help us make sure that we're not dominated by someone who's really got our number, whereas maximizing the average might be better when we're trying to figure out against a player we know nothing about what would be better. And maximizing versus tight or loose will help us figure out some sort of how to capitalize on the reads that we're making. So when M is 1, which is over there, no matter what the scenario, you should be pushing 100% of the time. That's what this is telling us, which shouldn't be a surprise based on all the stuff I told you about 1M situations. No matter what kind of assumption we're making, push 100%. So let me click up to M is 10. So what's going on here? So as M increases, like they all kind of move at the same time, except what? Like if we're targeting loose or we're targeting like best worst case scenario or best average, like it starts to trickle down to like 50%, right? But it's certainly like they're relatively near each other. And what's good about this is that means that if we target any of these, we're basically in the ballpark where like the difference between this column and this column for any of them is going to be not that material. Like if you are just in that ballpark, you're fine. But which one of them is completely different? Yeah, against a tight player. And it should make sense intuitively why, if you read him as tight, as someone who only calls 15% of the time, even with 9 and 10M, you should push 100% of the time. Why? It's because 85% of the time, he's just going to fold. And even when you're called, the amount of value you get from him folding most of the time just crushes him. So you should give, like to the extent that you can encourage him to be tight, do it, but absolutely, if he's tight, push every single hand. You're never in the scenario where pushing less than top 50% is good. So that's it for heads up. So now let's talk about other positions. And we end up in a lot of complicated situations, which we have to kind of just assume away here. Like, so we can lose in two different ways. We can lose if we call and he beats us, or we could also lose if we call and then someone behind us calls. So we're estimating that someone behind us is only going to call if he has a premium hand, because if we're in a short stack situation, someone pushes and then we call, someone's only calling behind us when they have a really good hand. And let's just assume we're going to lose if we get another caller. Like we are almost certainly going to be dominated. Let's say we have 0 EV there. And because of our equation here, we can actually solve that. We can actually figure out what range is going to be 60% versus another range. So this is resulting in a really cool rule of thumb here, which is when you're in a 10M or less situation and you're trying to decide whether to call an all-in, you just ask yourself, are you calling such that his range is 3 times more than your range? And some questions you might ask yourself is, say that you have ace-10, like you have a 10% range here. Would he push all in into you with king-jack, something in the 30% range? If you have king-queen, which is like 30%, would he push all in with like 8-5, which is 50% range, and so on. So when you're in a full ring situation and you're trying to decide whether to call, figure out, in general, what do you think his pushing range is there? And it's a good call if your calling range is 1/3 of his pushing range. Okay, cool, let's call it a day. Thanks, guys.